We ended our last video talking about current carrying loops of wire in magnetic fields. Let's take a closer look at that. And we'll use a nice square loop of wire carrying a current I. And let's take a look at each side. What's the magnetic force on just the top side? Just this section of our current carrying loop. It's equal to 0 because the direction of the current is in the same direction as the magnetic field. Let's take a look at the right side. Now we're looking at this section right here. We want to know what's the direction of the force on that section right there. Let's give the box some dimensions. Let's say it has a side D and current I. So the force is going to be equal to I times D times B, and the direction will be out of the page. The bottom section is also 0. Because the vector cross product gives us 0, the current is in line with the magnetic field. They're in opposite directions, but they're in the same orientation. And the last side of our box, the left side, has a magnetic force acting on it of I dB into the page. We can add these up and we get the net force is equal to 0, as we said in the previous video. But what is there acting on our loop of wire? There's no net force, but there is a net torque. If we take a closer look, we've got a force coming out of the page on the right side and going into the page on the left side. So what's going to happen to our loop? It will rotate. Let's take a look at this one more time, but in a little more detail, because we want to be able to calculate the torque on this loop of wire. First of all, I'm going to change it from a square to a rectangular loop of wire, so it's a little more general. I'll call the width W and the length L, as you can see in my side view drawing. And if we twist this view around 90 degrees and look down from the top, we can see the current coming up this side is coming toward us when we look down from the top. And the current going down the right side is going away from us when we were looking down from the top at this loop of wire. We've already done this in the previous example, so I'll just fill in real quickly. The force on the top and the bottom are 0. And the force on the left and right sides are equal to ILB. The right side is out of the page, the left side is into the page. And of course, that left us with a net force of 0. In this configuration, let's calculate the torque. This turns out to be the maximum torque on our loop of wire. We'll talk more about that later. The left side has a torque that's into the page, or from our top view, it would be towards the top of the page. The right side has a force out of the page when we look at it from the side view. But if we're looking from the top view, the force is towards the bottom of the page. The loop of wire is going to twist about its center point. Like this. So the lever arm is half the width of our loop of wire. Torque is force times lever arm. And that just includes one of the forces on the left side. We also have a force on the right side. We add those up and we get ILB, that's the force, times W. You'll notice we have an L times W. L times W is just the area of our loop of wire. The current times the area of the loop of wire times the magnetic field strength. Let's take a look at what happens as this loop of wire begins to rotate. We start out in this orientation and we turn a current on. Those magnetic forces act on this current carrying wire and cause it to twist or rotate. So an instant later, we have this situation. Our loop of wire has moved, has rotated a little bit. What's the direction of the force on the left side? It's still into the page. Or if we're looking at the top view, towards the top of the page. On the right side, it's still out of the page, or from the top, it looks like it's pointing toward the bottom of the page. Our torque now is a little bit less because the lever arm is a little bit shorter. Our lever arm is now W over 2 times the sine of theta. What's theta? Well, it's the angle we get from the normal to this loop and our magnetic field. Remember, in physics, we often use the normal to a surface to define the surface. There are an infinite number of vectors in this plane of the surface, but one vector perpendicular to the surface defines that surface, and we can use that to define our loop. We know torque is a vector quantity and it should have a direction associated with it. We can get that direction if we use a cross product. A is the area vector, and it points perpendicular to the loop of wire, and its magnitude is equal to the area of the loop. In this case, our wire loop is rotating clockwise as we look down from above. It's rotating clockwise. And the torque equation would tell us A cross B, A points in the direction of the blue arrow, A cross B points into the page. And if you put your thumb into the page, your right hand fingers rotate in the clockwise direction. So the torque is causing clockwise rotation when it points into the page. Remember, torque points along the axis of rotation, and our right hand tells us what direction the rotation is caused by that torque. If the torque is coming toward you, you put your right thumb toward you, and your fingers roll in the counterclockwise direction. So if the torque points toward you, it would cause something to rotate counterclockwise. If the torque points away from you, it causes clockwise rotation. At this point, we'll define mu, the magnetic dipole moment. Equal to the current times the area vector. So the torque on a current carrying loop of wire, mu cross b. And this is true if our loop of wire just has one turn, one loop of wire. Often we want to have a lot of torque. And so instead of just having one loop of wire, we'll wind it around and around and around. And so we have many loops of wire. We call those turns, many turns of wire. So for multiple turns, we just multiply by the number of turns. Capital N is the number of turns. An instant later, our loop is continuing to turn because there's a torque causing it to turn. And at some point, it's rotated by 90 degrees. What direction is the force on the upper side of our loop? When we look down from the top, towards the top of the page still. And on the bottom side, towards the bottom of the page. So what's the torque acting on our loop of wire now? At this instant, there is no torque. The torque is zero. The top side is being pulled up, the bottom side is being pulled down, and when I pull like that, nothing happens. But if it's like this, if it's rotated a little bit, and I'm pulling up on the top and down on the bottom, it rotates. I get a torque that way. But at this instant, I pull as hard as I can, and I'm not going to induce rotation. But our loop of wire has some rotational inertia. If it's rotating in this direction, it's going to keep rotating that way and go past this point. And now what happens? The torque is in the opposite direction, slowing it down until it flip-flops and starts to go in the other direction. And it'll oscillate back and forth like this. I want to mention that we have a right-hand rule for determining the direction of the area vector. You might be wondering, we had picked a vector that points perpendicular to the plane defined by that loop of wire. But we could have picked two directions, right? Pointing up this way or pointing the other way. And the torque would flip, give us a different answer. So how do we know what direction the area vector points? Our right-hand rule, this is the second right-hand rule we're learning. The first one was the vector cross product. That's the one we use most of the time. Most of these equations have cross products in them, and we use our right hand to determine the direction of the cross product. But in this case, we run our fingers around the perimeter of the loop of wire in the direction of the current. So if I have a loop of wire here with the current that flows in this direction, I wrap the fingers on my right hand. We have no left hand rules in physics, only right hand rules. The fingers on my right hand around in the direction of the current, and my thumb points out of the page toward me. So A, for this example, is out of the page. If I rotate it and point my current in the other direction, I wrap the fingers on my right hand around it in the clockwise direction, My thumb has to point into the page for me to do that. So the area vector would point into the page. And you can see from this situation, if I wrap my fingers around my rectangular coil of wire, my thumb points in the direction of the area vector.